Hello everyone, and thank you for joining today's talk on migrating Audible's media streaming infrastructure to Amazon CloudFront. My name is Ted Middleton, and I lead the AWS Specialized Solution Architects team for Edge Services, which includes CloudFront in the portfolio. Our primary speaker today is going to be Ronak Patel. He's a software development engineer with Audible who led the technical architecture and migration program that we're going to talk about today. Our goal today is to provide a technically focused discussion of how and why Audible recently undertook a very significant re-architecting project that included changes to their content creation streaming workflows, the underlying formats and protocols of their media content itself, and a migration from a legacy CDN to CloudFront. Here's a quick look at our overall agenda. We'll start off with a quick recap of what Audible is and what challenges they wanted to address with this project. We'll take a look at some of the specific technical considerations and the choices they evaluated. I'll come back on and provide a brief overview of CloudFront, focusing on some of the specific features related to media delivery, some of the optimizations in the platform, particularly some of those that were important in Audible's decisions. Then we'll dive deeper into how their new architecture works and some of the optimizations they were able to make along the way. And we'll wrap up by covering how they deployed, tested, and validated the ultimate outcomes and impacts on their users. We'll be taking questions via chat along the way, so go ahead and submit them there during the presentation, and our moderators will answer as many as we can via chat as we go, and we'll try to cover a few verbally at the end if we can. And with that, I'd like to hand it over to Ronak to tell the story.
Thank you, Ted. So Audible is one of the world's leading producers and providers of original spoken word entertainment and audiobooks. We have a wide variety of books, podcasts, originals, and exclusive content. So now let's dive a little deeper into what makes Audible unique. The main thing is just the length of our content. Our content tends to be tens to hundreds of hours long. Now, similar to ebooks, we use chapter breaks to organize our content and help our users navigate easily. Now, the good thing is that we're audio only, which means we tend to have relatively low bit rates. Now, these low bit rates are fine when it comes to single narrator productions, but Audible originals use music, sound effects, and dramatization to provide a rich immersive experience. Therefore, we'll want to increase audio quality for those originals so they sound really great. And finally, there's a rich set of devices and clients that we'll have to support. We not only have to support our in-house iOS, Android, and web clients, but third-party clients as well, such as Alexa. Now, these third-party clients impose quite a few challenges on us in that the upgrade cycles can be quite long, and we do not have full control on most of these surfaces. Next, let's dive into the use cases we'll have to support on AWS, carrying them forward from our previous CDN. The first is the ability for users to download and progressively play content on their mobile app. Second is the ability to stream full titles from the desktop web client. And third is the ability to create and play user-defined clips so users could highlight any important passages. And last but not least is the ability to stream content chapter by chapter so resource-constrained devices could keep a low memory profile while trying to stream our really long content. So here's a diagram that shows our previous architecture prior to our move. Now, we've been using this architecture for quite a while, but it started to show some rigidity in it when we were trying to add some new features. The first feature was trying to increase audio quality for our original content. Second, we wanted to use streaming as a primary consumption mode in our mobile apps, where most of our user base is. And this proved to be quite a challenge due to the way our streaming CDN worked. Our streaming CDN would create streams dynamically on demand, and it did this by downloading the backing MP4 asset from S3 down to the edge, and then proceed to transmux that MP4 into an MPEG-TS asset while creating a streaming manifest in parallel. Now, this process can be quite time-consuming since the performance is directly proportional to the size of that asset. And since the size of the asset increases with length and bitrate, we received quite a few complaints about timeouts and other kinds of generation errors. The other challenge that we face is the fact that we have duplicate infrastructures for our two consumption modes. We not only have a separate CDN for download, but we also have separate asset formats, and there's specialized code on all of our clients to handle a download versus streaming formats and consumption modes. And this adds quite a bit of development cost to our processes, as well as the storage costs of multiple kinds of assets on our CDNs. And last but not least, our transcoding pipeline and streaming CDN were not extensible enough to let us explore alternative codecs or alternative delivery mechanisms. So it forced us to make quite a few choices to work around these limitations. So in summary, here are the top challenges that we had with our previous architecture. First, we were getting quite a few reports of poor performance, leading to quite a bit of timeouts on our client surfaces. We also had an unacceptably high error rate on our old CDN, and this prevented us from using streaming as a primary consumption mode on our mobile apps. And last but not least, our existing solution was not extensible enough to let us innovate on our audio. So on top of resolving all of these challenges, we also had some additional design goals. The first thing was to make sure anything we built was going to be extensible to any new use cases that could come down the line. Additionally, since we wanted to use streaming on our mobile apps, it's important to try to reduce bandwidth consumption since users might be on cellular connections. And in addition, we had some non-functional requirements, such as increasing the visibility inside the health of our infrastructure, as well as reducing our development and storage costs across the board. Next, let's look at some of the technical considerations we had to go through to design our new system on AWS. So the first consideration was to finalize which media container we're going to launch. And as I mentioned previously, we used MPEG-TS on our previous CDN. Now, MPEG-TS is a popular container format to use for HLS streaming. It supports AES 128 encryption, and it's completely codec agnostic. Now, MPEG-TS comes from the broadcast and DVD world. This means that it not only imposes a fixed packet size, but it also has extra redundancy and error checking built into the format itself. This means it's going to have the highest container overhead of all of the formats that we looked at. Next, we looked at some elementary streaming formats such as AAC. Now, AAC also supports AES 128 encryption, and it also supports the AAC family of codecs, but it does not support any other codec beyond that. Now, since AAC is just pure audio, it has the lowest container overhead of any format that we looked at. So this is going to be the most efficient format to serve over mobile connections. And last but not least, we looked at the CMAF format. This is a format that comes from MPEG-Dash, and it's probably the most forward-looking format that we looked at. It not only supports industry standard DRM, such as FairPlay, Widevine, and PlayReady, but it's also completely codec agnostic, just like MPEG-TS. And in addition, it also supports modern delivery protocols such as HLS and MPEG-. Now, CMAF is also very bandwidth efficient, similar to AAC, but it comes close, but it's not completely as efficient as AAC. Now, since CMAF checked all of the boxes, we went into this thinking that CMAF was going to be the format we would launch with. But as we looked at all of the different clients we have to support, this turned out not to be true. So all of our in-house clients support MPEG- and HLS version 7 backed by CMAF. But if you look at the last row here, our third-party clients only support HLS version 4 with AAC. And this meant we were forced to deliver 3 new protocols. We would vend HLS version 4 backed by AAC and HLS version 7 and MPEG- backed by CMAF. Now, the good news is that all of our clients, in-house and third-party, all supported HLS version 4 with AAC. This meant that we could launch on AWS using this protocol, and we can cut over all of the client traffic from our old CDN to the new one without making much changes to our clients. Now, long-term, HLS version 7 and MPEG- is where we want to be, since it's going to be the most forward-looking protocols. And with that, I'll hand it back to Ted.
Thanks, Ronak. So let's talk a little bit quickly about CloudFront and Lambda at Edge and what they are and what they brought to the table. So CloudFront is a high-performance, globally scaled content delivery network, or CDN. It currently consists of over 220 different points of presence, or POPs. Those are located in more than 44 countries and over 87 different cities around the world. And CloudFront uses what we call a super POP architecture, which is instead of deploying infrastructure in thousands of different locations with just a few servers, we concentrate our infrastructure in high capacity locations where we can get lots of high quality, large bandwidth connectivity to lots of different network providers. So we're paired with thousands of different networks. We go to the major internet exchanges and things like that. We support techniques like hierarchical caching. So you have edge and parent tiers of caching. We have optimizations that really focus on cache width and cache retention and making sure that when a request comes in, there's a very high probability, over 95%, of getting a cache hit versus a cache miss. We also have techniques where we're able to locate content in the right places, intelligence about network performance and kind of the network internet weather map. And so we're constantly measuring the network and our infrastructure to make sure that any given request gets sent to the right place at the right time for the best possible performance. And lastly, that's all backed up by the AWS network backbone, which interconnects all our edge POPs back to AWS regional infrastructure. So you get really high performance, high reliability, and large throughput back to services that are running in the AWS infrastructure. So let's talk a little bit about some of the features and optimizations within the AWS cloud and within CloudFront that are primarily targeting media delivery applications. And we divided those into 3 sections. The first mile, which is how you get content into the cloud and into CloudFront. The middle mile, which is around distributing content out to the edge from the origins. And the last mile, which is about ultimately delivering content to the end user device. In terms of ingest and first mile optimization, there's a number of different features and services available in the AWS portfolio. Things like S3 transfer acceleration. So if you're ingesting content into S3 buckets, things like VOD assets, That helps with accelerating that ingest and make it highly reliable. We have Elemental Media Connect, which allows you to ingest content and distribute that to multiple locations within and without AWS infrastructure. It's primarily used for live signal acquisition. We have Direct Connect that allows you to directly peer and connect into the AWS network from your own infrastructure. So if you have lots of content or files in a CMS or things like that that you want to get into the AWS infrastructure or to applications, you can optimize that. We also, of course, have lots of different options for redundancy and regionalization. So if you want to localize content into different regions, you want to use replication, you want to use load balancing, there are tons of different capabilities that allow you to get the right content in the right place for the right audiences at the right time. With Elemental Media Services, there's a whole suite of products that allow you to do encoding, transcoding, packaging, manifest manipulation, and personalization. So again, turning content into streamable content, targeting users, doing server-side ad insertion, and other things around the content generation process. And last but not least, things like quality-defined variable bitrate encoding, or QVBR, allows you to get kind of the maximum amount of quality in the same amount of bits, or reduce the amount of bits for a given quality level. So there's a lot of different ways in which we can generate content. In the middle mile, this is where CloudFront comes in. So there's a lot of ways that CloudFront can optimize how we get content from the origin to the edge. We do things like use HTTP keep alive connections from the edge to the origin so that cache fills are optimally performed. We support things like chunks transfer encoding, and so this is really useful in things like live delivery or low latency applications. If content is still being processed by an encoder, it can still be delivered and streamed out to the edge. Again, we have techniques like hierarchical and regional caching. We use things like connection collapsing to make sure that we're not storming the origin or our mid-tier caches with lots of requests for the same content. We have a recently announced Origin Shield service that allows you to further collapse requests down to the most optimal regional edge cache in our infrastructure to your origin. And so that helps with, again, localization of requests back to the origin. We have a number of features around that I'm going to talk about in a minute around range requests. And that was one thing that was really important for the Audible solution. We'll talk about that in a minute. And then, of course, you can do things like negative caching and use short TTLs to on errors to protect origin from things like missing content or content that might still be processed by an encoder or things like that, so that you don't have to you don't end up overloading an origin for error conditions. And then in the last mile, when we're actually connecting to the client and servicing those connections, again, using things like connection keep alives, a lot of optimizations down at the TCP and network protocol layers, things like using BBR congestion control algorithms, packet scaling, HTTP2, so that you can do things like multiplex multiple requests onto a single connection. We support things like TLS 1.3 and 0RTT connection setup. So a lot of things that help optimize the way that we're communicating and transmitting data on the network. We have tons and tons of capacity, so more than 120 terabits per second of network connectivity out of the edge. A lot of that is direct peering with thousands of different networks. And we also, in some cases, embed POPs deeply within a major consumer ISP network. So we work with those partners to have POPs that actually deploy content directly into those last mile networks. Couple this with some perimeter protection offerings like Web Application Firewall and Shield, so that you can move your network and DDoS and attack mitigation surface out to the edge of the network, where you can take advantage of all the connectivity and processing power and infrastructure that AWS has. And you can block and mitigate typical types of DDoS and volumetric and other types of attacks before they ever hit your backend infrastructure. And then, of course, we have tons of features around allowing you to protect your content from unauthorized access, things like signed URLs and cookies, geo-blocking, field-level encryption, and other features that allow you to make sure that only the right users and authorized users have access to your content. One other component of the Edge portfolio with CloudFront is you have access to what's called Lambda at Edge. That's an edge computing platform that allows you to associate custom functions and custom business logic with different event triggers that happen within the HTTP request and response processing pipeline for CloudFront. So you get 4 opportunities to kind of execute that custom logic. One is when we receive a request before it hits the cache. You can do things like normalize headers, do URL inspection and transformation, device detection, various things on the inbound request metadata. If we end up with a cache miss where that piece of content is not in the particular edge cache that's handling the request, before we go back to the origin, there's another event for origin request. You can then do things like decide which origin you want to talk to, do regional load balancing, do failovers and things like that, retries. So there's a lot of different things that you can do in handling how you talk to your origin. Once we get a response back from the origin, you can inspect that response and do things like, some basic content transformation operations, again, response header normalization, maybe some different authentication response options. And then lastly, once we're ready to send the ultimate response back to the viewer, whether that was from within cache or something that went back to the origin, you can do all sorts of operations, again, custom header manipulation, things like that allow you to ultimately transform the response as it goes back to each user. And so this provides a really robust and rich platform for doing all sorts of custom logic at the edge with high performance. And Ronak will show some examples of how that benefited Audible's solution. And just one other feature to kind of key in on that was really important for Audible's solution, as Ronak mentioned, since they're looking at doing, moving to a streaming type of model and doing indexing of their monolithic encoded assets so that you can do things like bookmarking and chapters and seeking and scrubbing and things like that. There's some optimizations around byte range requests that are really important in a CDN. These deal with things like different devices having different behaviors and different support for byte ranges, doing some optimizations in the way that we retrieve byte ranges. So for example, if you're getting a lot of different range requests for different parts of an object, we can do background fetches for the entire object so that we're minimizing the number of cache misses that go back through the infrastructure into the origin, bring that object out into cache, and then service all those range requests from the cached whole object. We can do some things like range rounding and optimize the amount of data we're getting in a particular fetch. So there's a lot of different optimizations that we've made that we've seen kind of in the wild behavior to make sure that CloudFront can optimally service high request rate, byte range request oriented applications. So with that, I'll turn it back over to Ronak to go into some more details about their particular application architecture.
So let's dive into our new architecture on AWS. Let's go through all of the various areas that we had to change in order to make this work. The first area is the CDN itself. Now, the main thing we had to figure out was how are we going to generate manifests. Now, manifest generation is not only time intensive, but also it requires a good amount of compute power. Now, the good thing is that once you generated these manifests, as long as the path and any query parameters match up, we could reuse the manifest. And so an origin request Lambda at Edge function really fit this use case well. Next, we also implemented a custom auth scheme to protect all of our streams. And a viewer request Lambda at Edge function fit that use case really well. Next, we had to make significant upgrades to our transcoding pipeline. We not only had to support the new file formats, but we also moved all of the time-intensive compute out of the critical path of the user, and we moved everything here. And last but not least, we had to make changes to our licensing service to not only make URLs to CloudFront, but also to control the balance of traffic between our CDNs as we moved all traffic to CloudFront. So next, let's dive a little bit deeper into how we architected our CloudFront CDN. So on AWS, you have multiple options on how you can create manifests. The first is elemental, and then you can use custom options such as API Gateway or Lambda Edge. Now, elemental does not support audio-only streams or the really long content that we have. Therefore, we had to remove elemental as an option. And that left API Gateway and Lambda Edge. Now, the difference between these two services is primarily where the compute happens. With API Gateway, compute happens at the origin, and Lambda Edge happens as close to our users as possible. Now, you can actually deploy API Gateway in two different deployment modes. These are edge optimized, where you're using the CloudFront infrastructure to offload a request onto the AWS backbone as soon as you can. Or you can use a regionalized deployment mode, which will force users to reach back to your VPC directly. Now, we needed to figure out which of these two options we take, so we ended up creating a prototype. Now, on both of these options, we had to figure out how are we going to manually generate manifests, since we couldn't use elemental. Now, in standard video on-demand use cases, you can generally create all of your manifests upfront and then statically cache them on your CDNs, and your users can take advantage of that. Now, this is really simple, but it just didn't scale for us in our clipping scenarios since those are user-defined. If we were to do that, we would end up having to either pre-compute every permutation of every clip that could possibly be created, or we'd be creating brand new assets on the fly every time the user pressed done. Now, neither of those two options scale either. And therefore, we thought that if we could use a single asset to back not only clips, but also full title playback, that would be the way to go, because it's really simple. Now, this works because a clipping operation is nothing more than a byte range request inside of this larger asset. And so the main challenge was to export all of the asset metadata that we needed into a separate data store that our Lambda function could use to generate a manifest. And the most important metadata is the actual time to byte offset hash table that's present in an asset. Now, this hash table could be simplified into an array because our clipping operations only require a 1-second granularity. Therefore, we could use simple math in order to convert a clipping time and end position into a byte offset to select portions of this larger array. And then we can aggregate all of the byte offsets that are inside of this portion to create streaming segments. So now that we've figured out how are we going to create manifests, now it was time to run this prototype. And so we used a third-party tool such as Catchpoint to help us here by setting up a worldwide performance test. And so here are the results that we got from that test. So we tested a regionalized API Gateway, edge-optimized API Gateway, and compared it to Lambda Edge. Now, taking regionalized API Gateway as the control, we saw double-digit performance improvements compared to regionalized API Gateway. And this makes sense because the other two options run over the CloudFront network and does not force clients to go back to your VPC to make a request. Now, in addition, we saw even further performance enhancements when we used Lambda Edge. And in particular, we saw a double-digit improvement in many different regions around the world. Now, since performance is our key design tenet, that pretty much sealed the deal on using Lambda at Edge as our solution. So now that we selected a manifest generation option, now it was time to figure out how are we going to get asset metadata to the Lambda. And here we looked at two different options. First, we looked at DynamoDB global tables, and we compared that to storing flat files on S3 and downloading them to the Lambda. Now, in our performance comparisons, both of them were pretty even in terms of performance. And so the simplicity of the flat file option ended up winning out. Now, even in flat files, you have multiple encoding options. You can use a binary file format, or you can use something text-based. And we ended up choosing a binary protobuf file format since it has a fast decode, it's really compact, and it uses schemas so that we could extend the file in the future. Now that we figured out how are we going to get protobufs to our Lambda, it was time to start not only developing our Lambda, but trying to optimize the way that it runs. And the first thing we could optimize were the network calls that we made from our Lambda. And the first thing we looked at optimizing were all of the non-obvious network calls. These are all the network calls that your Lambda makes, which are not directly influencing your main algorithms, but are there as well. So in our case, we were making calls out to CloudWatch and Secrets Manager. And the way we optimized those were to make sure those calls were made in region, so the Lambda function was not reaching across region, slowing the Lambda down. And next, we had to figure out how are we going to retrieve these protobuf files. Now, our transcoding team were kind enough to set up two different buckets to host our protobuf assets. So we had a primary S3 bucket served out of Virginia, and we had a fallback bucket served out of Dublin. Now, we also took advantage of the CloudFront origin failover feature to set both of these buckets as our origin. Now, if you focus on the Lambda function running in South America, you'll see that it makes sense for this function to reach out to Virginia as the primary origin, since Virginia is geographically closer to South America. And then if something were to happen, it can fall back to the Dublin origin. But if you look at the Lambda function running in South Korea, we may want to swap the order, since Dublin is a lot closer. So we actually implemented custom logic in our Lambda to first reach out to Dublin and then fall back to Virginia. And in addition, we also figured out that these protobuf files are actually immutable and only used to actually create manifests. Therefore, we could actually cache these protobuf files directly in the Lambda, and we can actually save on these extra networking calls. So let's look at a snippet of our actual Lambda code so you can get an idea of how this worked in code. So I'm showing a snippet of our index TS file. Our Lambda is actually written in TypeScript. So on the bottom here is the Lambda entry point where on every single invocation, this function is going to be called. When at container initialization time, the Lambda container will run your entire index TS from top to bottom. So this gave us an opportunity to run a bunch of logic up front. So we took advantage of this by initializing all of our AWS service objects. And as you can see, we took advantage of the TCP keep alive settings to save on TLS and TCP handshakes. We also set the options for the region. So we made all of the network calls in region. We also took advantage of modifying the number of retries that we make to try to keep performance up. And in addition, here's where we implemented an LRU cache to keep our protobuf files cached in memory inside of the Lambda container. And we used an LRU cache to make sure the most popular content was available in this cache, so more of our user base could enjoy better performance. Now, as we were working on our Lambda code and trying to optimize it, we observed another optimization that we could take advantage of. Now, if you were to draw a comparison between the length of our content versus the manifest size, we saw that as the length of our content increased, so did the manifest size. And because the size of the manifest increased, the time to generate that also increased. But if you were to increase the segment size, not only does the manifest size go down, but the generation time goes down as well. And on the bottom here, I show a table of two different assets and the performance that we saw with them. Now, on our previous CDN, we used a 10-second segment size. And we initially thought this is what we would go with on AWS as well. But we realized that there was actually issues that were happening on our previous CDN with devices like Alexa. So since Alexa is resource constrained, it cannot support manifests greater than 1 megabyte when they are uncompressed. Therefore, we had to increase our segment sizes to 20 seconds just to accommodate. Now, this ended up being in our favor because manifest generation time was cut in half, as well as our manifest sizes. Now, there is a trade-off here in terms of time to first play, because the player has to download twice as much audio data in order to start playback. But we kicked this particular concern down the road until we could do real performance tests to realize the impact. So next, let's dive deeper into our transcode pipeline. So here are the 4 major steps that are involved in any transcode pipeline. And the first thing that we did was to replace our packaging step. And we replaced it with a packager that could create our AAC and CMAF assets, could also support our current and any future set of audio codecs we may want. It can also support industry standard DRMs that we may want to implement in the future, and was performant enough to generate our largest content in a matter of minutes. Next, we introduced a second step in our pipeline to generate protobuf files from those aforementioned assets. And lastly, we replaced our validation step to make sure that the protobuf file and the associated asset could be used together to not only create a proper manifest, but that the clients could actually play them. And we did this by mimicking exactly how a client would work. So we ended up using the protobuf file to request segments from the asset, and then we ended up decoding the audio inside to make sure everything was A-OK. Now let's dive deeper into the actual integration and rollout. So as soon as we were dev complete, the first thing we did was launch a performance test between our previous CDN and our new setup. And we did this by taking advantage of that third-party tool, Catchpoint. And we set it up to compare both CDNs over ISP backbone networks. And we did this so we could eliminate any variation in end user networks from our results. Third, we also selected a representative set of assets varying the duration and the bit rate so we could get a more accurate reading of our performance. Now, a big lesson that we learned from this step was to make sure you tested the same flow on both CDNs. We made this mistake often by testing different portions and which threw our results out of whack. Therefore, to help save you time, make sure that you set up your test properly and you're measuring the right things. So once we figured out our problems in our tests, here are the results that we saw. So we saw that CloudFront, our CloudFront setup, was actually significantly more performant than our previous CDN. We're seeing performance improvements anywhere from 20 to about 55%, depending on the region. So this told us that we were definitely on the right track. Now, once that was done, it was time for final QA and rollout. And so our in-house mobile clients turned out to be really easy to test, and we ended up making no changes to them at all. We had to make a minor change on our web client to swap out an incompatible player with one that was compatible with our new AAC-based streams. Our biggest time was spent on Alexa and other third-party clients. We faced numerous issues with them, and we were forced to deploy over-the-air updates to fix client-side issues on all of these platforms. Now, as I mentioned earlier, these platforms can take a long time to actually upgrade. And so we could actually decouple our CDN launch from these clients. We ended up installing a device list inside of our licensing service. And our licensing service would consult this list to determine which CDN a particular device should go to. Second, we also installed an A/B test inside of that licensing service, so we could start taking performance measurements on the devices that were on CloudFront to determine what the performance was like. So once we got to the point of 50% cutover between the two CDNs, here's the performance that we observed. So with our 20-second segment sizes, we noticed actual degradation in performance in the average case for those clients. And this forced us to revisit the segment size decision that we made earlier. And so we ended up deciding on using a 10-second segment initially so that it would force the users to download less audio so that playback can start faster. And just by doing that change, we noticed a 9% swing in performance in the positive direction. And so this was the final setup that we used to launch our CloudFront CDN migration. And with that setup, we ended up launching Audible's brand new Audible Plus offering not too long after that. Audible Plus is our new all-you-can-listen service that's included in any Audible membership, and it gives access to users to not only podcasts but expertly curated audiobooks. So here is a graph of our traffic profile after our cutover to CloudFront. And the graph here is showing our request count over time. Now, if you were to look at the first main milestone when we went to 100% launch, you'll notice a blip that happens after that. That blip was because of additional issues that we found on some Alexa devices. So we ended up using our device list to push those Alexa devices back on the old CDN until those issues could be resolved. And then after that, we were pretty much smooth sailing all the way up to the launch of Audible Plus. And now we're pretty much at equilibrium. And our traffic profile is now orders of magnitude more than we were at 100% launch. Next, here are the cache hit ratios we were able to attain on CloudFront. So at 100% launch, we were doing around 93 to 92% cache hit ratio. But once Audible Plus launched, that actually boosted our cache hit ratio to 94 and close to 95%. So in conclusion, here are the results we were able to achieve. With this new setup, we've actually delivered over 20 billion hours of audio to date. We've also achieved significant improvements in time to play. and a significant improvement in our error rates. And to top it off, we also improved the bandwidth savings for all of our users to the tune of 300 terabytes per month. And last but not least, we've set ourselves up for future improvements in audio quality and other features as we go into the future. And last but not least, our user base ended up appreciating all of our efforts by leaving a really great App Store review calling out the seamless streaming experience that they had. And they gave us 2 thumbs up. So with that, I want to say thank you for listening to our talk, and we're ready to take your questions.